Now we're ready to move into Module 9.1 for the OLI book, where we're going to look at sampling distributions and the central limit theorem. The central limit theorem is one of the key theorems that allows us to make assumptions about large populations where we only have sample data about those large populations. So when we talk about large populations, we're talking about numbers that go with very large groups. Normally, if a number is tied to a population, meaning everyone has been counted, we call that number a population parameter. But many times, populations are way too large for us to talk to everyone or to poll or measure every item in the population. And so we instead choose to use samples rather than doing a full-out census. Samples can many times produce actually more accurate results than census data because census data is so difficult to truly conduct if you're going to do it in a correct manner. Samples end up being a lot less expensive and can actually be a good estimate of the overall population number, which we do not know. And of course, one of the ways we can always increase the accuracy of our estimations is to make sure that our samples are of large enough size. So let's look at this idea of a sample and kind of explore it. We know that when we take samples from populations, they're of course not going to be the same as what the number we might get from if we were to actually do a census of the population. And we can kind of look at that in just a small scenario. We could call a single statistics class a population. And if I were to pick 5 people at random from our class and found the average that they got on the last test, and so averaged all 5 of those scores, we would probably see that that number would differ from the true population number, which would be the mean of everyone's scores who took the test. So more likely than not, we know that sample number is going to be different than the actual population number. In fact, we would actually be surprised if the sample we happen to pick would be equal to the true population number. But let's say I did this sampling of 5 tests several times, let's say 10 times. And if I were to take all 10 of those sample results, those sample means, and I were to average all 10 of those out, we'd probably find that we're getting closer and closer and closer to the mean of the population. I could have also enlarged my sample, and my enlarged sample would probably end up getting a lot closer to the population number. So these are just some sort of common sense ways that we can use to improve the accuracy of our sampling. In fact, let's explore this a little bit more, and we're gonna tone down our population down to 5 people, and these 5 people are going to be the starting players of a basketball team, and we're going to look at their heights. So we have 5 people. This represents my population, the starting members of this basketball team. And so because it's such a small population, I can actually know what the target population number is, which is 80. If I added all those up and divide by 5, we find that the population mean for this really small population is 80 inches. All right, and then let's go ahead and explore what will happen and what type of results we'll get if I break this population down into samples of 2 and use that as an estimation of that 80. What we find if I take every possible sample, meaning we go A and B, A and C, A and D, A and E, and then B, C, B, D, B, E, and find all of those means, what we find is that we get a list of numbers here. One interesting thing is that we only hit the actual mean of the population once, but we're kind of jumping all around the 80 here, getting as far away on the left as 3 inches and as far away from the mean on the right by about 3.5 inches. And so this sampling distribution, when we talk about a sampling distribution, it is a collection of every possible sample from every possible combination of sample of size n. That's called our sampling distribution. Now, if I take this sampling distribution and I find the mean of all of these numbers, what we find is that the mean of all of those samples is actually equal to the population mean. In this case, the mean of all those actually comes out to be 80. So this leads us to the first part of the central limit theorem. And I give that illustration because this definition can be a little bit confusing. But what we're talking about is the sampling distribution, the table of values that contains every possible sample. And what we say is that the sample of size n, the mean of all of those x bars that we get of samples of size n, if we were to find every single one of them and add them all up and divide it by the number of numbers, we would find that the mean of the sampling distribution is equal to the mean of the original data, the mean of my population. And this works for every size sample. If I chose samples of size 3, here we have it. One thing I want you to notice is that now my numbers have become a little bit more accurate. I'm only down to the left. Again, I only hit the number once, but to the left I'm only down 2.3, and to the right I'm only away from it by 1. So the deviation of my numbers is getting smaller. They're getting closer and closer to that population number that I'm after. And if I take the mean of all these numbers, the mean of all these numbers is equal to the mean of the population of 80. And then if I have samples of size 4, again, we can see that we're getting even more accurate, less of a range between my lowest and highest on the lower end. I'm only off by about 1.5, and on the upper end I'm still off only by 1. And the mean of all these numbers is equal to the mean of the population. So this first part is more of a conceptual idea, a very important part of the central limit theorem. Let's look at the rest of it. For any given population with a mean and a standard deviation, a sampling distribution, right, a table of values that lists every possible sample with samples of at least 30 will have the following 3 characteristics. Number 1, the sampling distribution will approximate a normal distribution regardless of the original distribution. Let's leave this one here aside, but this is one of the most important parts of the central limit theorem. Secondly, though, the second part is what we just looked at. The mean of the sampling distribution equals the mean of the original data for the population in question. Now, this is something we also saw in the previous example. The standard deviation of the table that we create of every possible sample of size n equals the standard deviation of the population, but divided by the square root of the sample size. Here's a formula to kind of illustrate that. So this is sigma sub x bar. We see that this, the standard deviation of my sampling distribution, is not equal to the standard deviation of the original population, but rather that population standard deviation divided by the square root of n. Let's take another deeper look at this. So, important thing before I move on, though, I want to point out the mean of the sampling distribution is equal to the mean of the population. However, the standard deviation of the distribution is not equal to the standard deviation of the original population, but rather that standard deviation divided by the square root of n. So the mean is changing, the mean is staying the same comparatively, my original data table that we create. However, the standard deviation is getting smaller. We can see it in this picture. Here's a picture of the original heights spread out, and here's the mean of those heights. So this represents n equal to 1, sample size of 1. That means my original data. The mean of all these numbers was 80. And we saw for samples of size 2, the mean did not change. The mean of all these numbers is also 80. But notice how they're getting closer to the blue line. As they gather closer to the blue line, that means that the average distance each data value is straying from that line is going down, and it goes down in a very systematic way as we go down here until we have samples of size 5, which would represent my entire population. So as the sample increases, the points seem to gather around the blue line, which is my mean. In other words, my standard deviation is going down. We also can see that in this picture here by Q-scores. This is my original data. Once I have a sample of size 4, the standard deviation of my data changes from 16 to 16 over the square root of 4, which is 2, which gives me 8. And with samples of size 16, again, we see that go down. 16 divided by the square root of 16, which is 4, which leaves me with a standard deviation of 4. And so my numbers are gathering around that center point of 100 as we go and increase our samples. So for example, if we had a population standard deviation being equal to 9, and then we create a sampling distribution from that population with samples of size 100, what would be the standard deviation of that table of values? We can easily calculate that by going sigma sub x bar is my original sigma, 9 divided by the square root of 100, which is 10. So the table of values would only differ from the mean on average of 0.9 units as opposed to 9 units, which was how far they deviated from the middle in my original population distribution. Let's go over this. That's just another example. All right, and so the central limit theorem, let's go back to that first part of it that I said, let's put this off for a minute. Now we're going to come back to it. Another part of the central limit theorem stated that the original distribution was irrelevant and that the distribution of the means will be normal, meaning it'll follow into an approximate normal distribution as long as the sample sizes are greater than 30. So I want you to look here. We've discussed different types of ways that populations might distribute themselves. We have uniform distributions, we have skewed right distributions, we have populations that are normal for their original data. But regardless of how it looks originally, as we kind of go down the list here and get samples, once we hit a size of about 30, it actually doesn't matter at all how the original population data was distributed. Those sampling distributions, the means that we pulled out from our population, every possible sample, approximate a normal distribution. And so that's pretty powerful. It means that we don't even have to have a normal distributing of our data. As long as we take samples that are 30 or greater, we can know that those means that we collect will behave in a normal fashion. And in fact, if we started out with a normal distribution, we don't even have to have samples of size 30. No matter what the sample size is, we always get a normal distribution of those samples. So when we go to solve word problems, we change our procedures slightly, knowing that when I take samples from populations, the standard deviation isn't going to be what it was originally. It's going to change. But we're going to use the same basic procedures that we used previously in modules 8.4 and 8.5. First, we're going to draw a picture and label the curve according to the parameters that we're given. And then we're either going to use normal CDF or invert norm. We're going to use normal CDF if we're after a probability or an area. And we're going to use invert norm if we're after a value along the horizontal axis, our calculators, matching what we are entering to the graph we've created. We want to note, however, and this is a big note, that for a sampling distribution, meaning we've taken a sample from a population, that the distribution of those samples of size n is going to have a very different standard deviation. And that standard deviation is sigma sub x bar equaling sigma of my original data, x, divided by the square root of n. Then we're going to answer the question posed using complete sentences and or phrases. Now, if we're after a z-value, sometimes we're just wanting to know how far something is standard deviation-wise away from the mean. That's when we want to calculate the z-value. I want you to take note that this also has changed. Now we're talking about not just an x, but we're talking about x bar. We're talking about the standard deviation of the population. And so we need to take the original standard deviation and divide it by the square root of n. Entering this into your calculator can be tricky. You want to make sure to actually put parentheses around the top and also around the bottom quotient. So let's look at an example. A population has a normal distribution with mu equal to 50 and s equal, I'm sorry, not s, but sigma equal to 10. We intend to draw a sample of size 100. What is the probability that that sample mean will be greater than 52? So in this case, what we want to do is, again, we're after a probability. So we're using normal CDF. We're going to put 52. We're going greater, so that's our lower boundary. 1,000 is on the right. Our mean is 50, and our standard deviation, notice I'm not just putting 10 here, but rather 10 over the square root of 100. And we get 0.0228. We're doing less than 48.5. Now we're going less than a number that is to the left of the center. So we're going normal CDF negative 1,000 all the way up to my upper boundary of 48.5, comma 50, comma, again, the same thing, 0.0668. And if we're going between these two boundaries, again, we're just still after an area here. We're going to go normal CDF 48.5 all the way up to 52. We have no unbounded sides of my curve. We have two definite boundaries. And we find the area to be, or the probability to be 91.04. This comes to the end of this. We're going to go through more examples in the second half of this slide presentation.